About the wind forecast, actually, we are really familiar with this topic. And traditional methods mainly focus on the point forecasting, just like the left picture shows, and which calculate the expected value of the wind power output in the future. However, due to the inherent uncertainties and random of the wind resources, invulnerabilities variation may appear. And on the left picture, more and more attention are paid to the probabilistic forecasting, which is better quantifies uncertainties of wind power output in form of quantized and prediction intervals. Density functions has received much more attention in power system. So we do the probabilistic wind forecast. However, here the problem, and we all know that under complex and variable weather conditions, and we actually we have many data analytics and AI models introduced in this area, and the left picture gave a review about the methods application in the wind forecast, especially the probabilistic wind forecast. And we can find that actually uh, most of the models they are trained based on the historical scenario with inherent network structure and parameters. And that means, and once we got the network structure and parameters, and then it is designed to do the work to do the wind power prediction. And however, the wind situation change timely and under complex and variable weather conditions, we use the fixed network structure and parameters to do the future wind forecast. It has the limitation, and we do the compression analysis. It's really is low adaptability and generalization capability for future scenarios, especially in the right the down pictures, and we show the cold wave extreme weather wind situation. Actually, especially under the extreme weather conditions, the fixed network structure and parameters will has a bigger limitation. So the idea is that we are bringing the transfer learning uh, and to do the adaptive probabilistic wind power prediction. And actually, the idea is that we want to do um, we want to we want to how to say uh, like the model do not have the limitation about the fixed model and parameters, so we bring in the model-based transfer learning to optimize the network structure and improve the nonlinear fitting ability of the original network. Actually, we do the work based on the ERM is a really familiar model extreme learning machine. So the model-based transfer learning is used to construct the multi-layer extreme learning machine. And also, meanwhile, the output mapping factors of the multi-layer extreme learning machine are further optimized through the particle swarm optimization with the objective of minimizing of the quantile evaluation index. And about the idea, the second part is that we introduce and bring in the future transfer learning to do mine the intrinsic feature representation from the time series wind power output, and then the network parameters are effectively updated to improve the adaptive of the model parameters. So the joint distribution adaptation is utilized to explore historical temporal variation characteristic and update with of the multi-layer extreme learning machine to accommodate variable and wind power output. So the right picture gave the the framework of the proposed method. And in the first part, the multi-layer stream learning machine is constructed through the model-based transfer learning, and feature inputs are historical wind power output, while outputs are quantized wind power output to be forecast. And then the output mapping factors of the multi-layer stream learning are further optimized through the particle swarm optimization method with the objective of minimizing quantity evaluation indexes to enhance the quantile regression results. And finally, the weights of the multi-layer stream learning are updated by the GDA from the feature-based transfer learning, take the weights and the historical moments as training data sets to adapt to variable wind power output. Actually, this is the key three steps as I introduced. We construct the multi-layer stream learning, and we do the parameter optimization. And finally, we update the weights based on the feature transfer learning. And more details can also found in my papers. And here are some test results. And actually, we cooperate with the biggest wind farm in China, and that is the Jibei wind farm. And the data quality is very good. And we do the test, use the data resolution for 15 minutes. And here is the model optimization effect based on the transfer learning. And this is the three kinds of results to show the three steps results. And from the left pictures, we can see that using the model transfer method, the quantile regression results decreased to 75% to 90% of the initial value during the transfer process. And in the middle picture, we can see that after optimizing the multi-layer stream learning machine using particle swarm optimization method, the evaluation indicators can be optimized by 10% to 33%. And finally, there's a significance in the width of the multi-layer stream learning machine for adapting to wind power output characteristics at different time periods. And the proposed method can improve the model's parameter self-adaptability. So the right picture shows the updated weights about the multi-layer stream learning machine. We can clearly find that we really need to update our model and parameters once the time passed by. Yeah, and here are the results to show the real calculation results about the wind power probabilistic prediction. And actually, the left picture show the predict results, especially about the probabilistic forecast results. And we can see that we can accurately do the forecast task, and especially and during the results, actually we give the probabilistic results, and actually the actual wind power output, and that's the yellow line, and we can see that all the actual wind power output located in the results what we obtained. And meanwhile, we can do the accurate and reliable quantity prediction results. It can be obtained for peak and value nodes. Now, meanwhile, we also do the comparison with our method and also with the other classic methods, including the BPN, NCN, LSTM, and also the extreme learning machine. And we can see that actually the reliability metrics and skills metrics are better than the other methods. And however, once we got actually this method proposed before the cold wave event happens, and once this cold wave happens, and we got the data and we test in the transfer learning, I think we found that actually the results is still good. However, it's not to however, it's not the our expected results. So we can see that actually in practice, abandoned training samples are playing critical role in the effective training process of existing forecasting models. So considering extreme events with low probability parity, the scarcity of relevant features measurement cannot meet the numbers of training samples required, which severely limits the effective training process of the model, making the accuracy of existing forecasting model significantly under extreme events and posing great challenges to generalization capability. So the idea is that we introduce the reinforcement learning to realize effective data enhancement and optimize model parameters adaptively. The general framework is given here, and actually there are three key parts. We evaluation index for the mutation characteristic and extreme events is constructed. An error evaluation model is then established with quantity regression loss function introduced, and the index takes as the benchmark. On this basis, the data metric strategy gradients based on quantity fitting model is proposed with the aim of minimizing the long-term error feedback, where experience replay pool is utilized to establish effective training samples under small data size by extracting key historical transition and model parameters are updated through the small bench learning. And we do the test case on the practical situation, especially based on the real code with weather data. And we can see that and knows with legitimate sudden changes in output, the quantifiers obtained by the proposed methods can effectively include the actual wind power output, even in extreme scenarios. We also do the comparison analysis actually in the conventional, and that means not the extreme weather conditions. Um, the reinforcement learning is slightly better than, but close to transfer learning, but both indicators are far lower than the other methods. But in the extreme scenarios, the reinforcement learning targeting extreme scenarios can achieve better probability prediction results. So this the first kind of work. And